night drift into the darkest architecture of the universe. Black holes shape light without shining. They carve shadows, spin luminous disks, and launch vast jets into the void. In this sleep-calm journey, the event horizon becomes a boundary of pure physics, and the cosmos speaks through bending starlight and distant ripples in space-time. If this kind of deep, soothing science is your place to unwind, tap like subscribe and turn on notifications. This is deep space drift. Now, let the universe slow down. A black hole begins as a quiet absence. It is a region where light fails to return. A thin rim can still appear around that absence. The first scene holds a dark circle inside a narrow ring. The ring looks almost steady. The darkness looks complete. A calm hook sits in the contrast. Something unseen becomes visible by what bends around it. The early anchor follows at once. A black hole is described by its boundary and by nearby light, not by a view inside. The event horizon is a boundary beyond which escape routes vanish. It can be pictured as a river mouth hidden in thick mist. The water surface stays smooth until the final moment. Past the mist, the river drops and no driftwood returns. At the lip, the current still looks ordinary. Small ripples slide onward with no sign of the drop. After the fall, no surface pattern returns upstream. The change is not a wall. It is a direction that no longer points outward. That boundary matters because it sets the edge of what outside light can reveal. At this distance, darkness does not mean emptiness. Gravity still shapes the space around the center. Light follows the straightest available route. Near a black hole, those routes curve. Starlight that would pass beside the center bends inward. Some rays swing around and leave again. Some skim so close that they loop once before escaping. A band of brightness forms where many near-miss paths gather. The ring is not a material hoop. It is a stack of curved routes seen all at once. A small unlock rests inside this geometry. The dark region is larger than the horizon itself. It is a shadow made by missing directions of light. The shadow edge depends on how close light can pass. It is shaped by curvature, not by any surface. A slight change in the angle of approach reshapes the bright arc. The ring is the bright border where paths pile up. Closer in the ring gains texture. The bright rim is uneven. One side can look brighter than the other. The difference comes from motion in glowing material nearby. A second scene appears behind the rim. A faint, flattened haze circles the dark center. Gas rarely drops straight inward. It keeps sideways motion and spreads into a rotating layer. An accretion disk is a hot rotating layer of gas around the hole. It resembles fine silt swept into a slow spiral in a sheltered bay. Thin lanes form and fade as the flow tightens. The disk can look layered. A brighter inner band sits inside a dim outer skirt. The bands drift like cloud decks stacked at different heights. The spiral matters because it provides the light that outlines the shadow. Within that glow, another payoff settles into place. A black hole does not need to shine to become known. Nearby matter can supply the brightness, then gravity reshapes it. The disk does not glow the same everywhere. The outer region stays cooler and dimmer. The inner region becomes brighter and sharper. A smooth gradient forms across the disk face. Brightness increases toward the inner rim. The inner edge never becomes a hard wall. It becomes a blur of fast orbits and rising heat. Light from that region leaves with a changed tone. It climbs out of deep gravity and arrives stretched and softened. The change is not a decoration. It is a clue that the light departs from a steep gravitational slope. A visual anchor returns as the disk light meets the curved paths. Some rays curve behind the hole and reappear. Some skim along the rim and linger. A thin ring grows brighter where these paths cluster. A scale shift steadies the mind. For a black hole with the mass of a star like the Sun, the horizon spans about 3 kilometers. That is like the rise from the ocean's surface to a high mountain summit. The number sounds small against the sky. The influence is not small. Far outside that narrow edge, light still bends. A wide background starfield can be nudged into gentle arcs. Some paths wrap into partial rings. Some paths fold into short streaks. Minutes of motion near the inner disk can correspond to years of drift farther out. The mind expects size to match reach. Here, reach belongs to curvature, not to the diameter of the horizon. Another small unlock settles without strain. The event horizon marks a local rule. The visible signatures extend into a much larger neighbourhood. In that neighbourhood, intuition meets a clear limit. The horizon cannot be watched as an object crosses it. No outward light marks the moment of crossing. Only outside light can be traced. Even that tracing has limits. Many bent paths overlap before they leave the region. Their light blends together. Fine detail cannot always be separated at immense distance. The ring can blur into a thicker band. The shadow can look softer than the true geometry. Thin gas and dust between stars can scatter light and smear edges. A signal would carry only what survives this mixing. The interior remains inferred, not observed. Even with that limit, the patterns remain persistent. A dark centre inside a bright rotating layer repeats across many settings. Changes in disk brightness carry timing clues. Fast flickers suggest tight orbits close to the horizon. Slow waves suggest broader flows at larger radii. The ring shape carries geometric clues as well. A nearly circular rim suggests a stable central mass. A crescent suggests brightness gradients and motion in the disk. Different arrangements can paint similar shadows. That ambiguity is another limit of observation. It is a limit of inference where multiple causes fit one image. Still, a reliable path remains. When several clues agree, the picture becomes firm. The final scene of this section pulls back again. The ring rests around darkness. The disk glow fades into a thin haze. The starfield beyond stays quiet and deep. The boundary remains a concept, not a visible surface, yet it shapes every route in its neighbourhood. The next step turns this picture into a rule. Gravity is not only a pull across distance, it is a change in how space and time guide motion. In the coming section, the same bending that shapes the ring becomes the main language of explanation. A field of distant stars looks still, yet their light can arrive along curved routes. The bend comes from the shape of space and time near mass. In that region, gravity is not only a pull, it is a change in geometry that guides motion. The first scene is wide and quiet. A dark region sits near the centre of view. Behind it, a thin arc of starlight appears. The arc is pale and clean. It resembles a thin band of frost on dark basalt. The arc does not cling to any surface. It hangs in empty space as a trace of curved travel. Light behaves as a messenger that follows the route available. Even when the speed stays about 300,000 kilometers per second, the route can still curve. That speed is like about 7 times around Earth in a single second. A small unlock settles early. A bend in light does not require a push on the ray. It can arise from the shape of the region the ray crosses. The next checkpoint is the idea of the straightest path itself. Geodesic is the straightest path that curved space allows. On a flat plane, that path never turns. On a curved surface, the same rule can create a gentle arc. A smooth pebble rolling across a shallow hollow in hard clay drifts into the low line and stays there. The pebble does not decide to turn. The ground shape sets the turn without any touch from outside. This matters because starlight follows geodesics in the same calm way. The path is shaped by geometry before any bright rim is seen. A second scene arrives closer in. The star points behind the dark region no longer look like points. They stretch into short streaks that curve around an unseen centre. Some streaks are brighter at one end. Some fade at the tips like smoke thinning in still air. The brightness gradient is a clue to how many paths overlap. Where many near-miss routes gather, the arc brightens. Where fewer routes pass, the arc thins into darkness. Another unlock appears in this layering. A single background source can be split into more than one visible image. A pair of faint points can appear on opposite sides of the dark region. Between them, a soft arc can connect like a strand of diluted light. This is not duplication by reflection. It is one source seen along more than one curved route. Gravitational lensing is light bending that reshapes distant sources. A calm analogy fits this reshaping. Moonlight passing through high ice crystals can form a pale halo. The halo is not a ring in the moon itself. It is a pattern created by many refracted paths through the air. This matters because lensing turns geometry into a visible signature. When alignment becomes closer, the arc can lengthen into a nearly closed loop. The loop is thin and fragile. It can look brighter on one side and dimmer on the other. The unevenness comes from the background source shape and from uneven overlap of paths. A quiet payoff follows from this loop. The loop radius depends on distance and mass, not on any hidden surface. It is geometry made visible as a circle of light. Even a small change in alignment can break the loop into separate arcs. The breakup looks like a ring torn into drifting petals. The petals stay locked to the same invisible center. The signature can be read as shape and sometimes as timing. A third scene begins as a slow pulse. A distant glow brightens, then fades into the background. After a pause, the glow returns again. The repeats are softer each time. The cause is not an echo in a medium. It is a set of arrivals along routes of different length. One path travels closer to the center and curves more. That path can be longer in distance even when the start and end are the same. The extra travel time can spread a flash into a gentle sequence. A small payoff follows from this delay. Time itself becomes part of the map. Changes in brightness can hint at how deep the slope is near the center. At this distance, a signal would carry only the blended result of many threads. The threads cannot be separated one by one. That is a clear limit of observation. The finest bending happens on angles that can be too small to resolve. Several different mass layouts can create nearly the same arc. A smooth distribution and a clumpy one can mimic each other in a blurred image. Dust and thin gas between stars can also scatter light. Scattering softens edges and rounds sharp corners into haze. Timing can help, yet timing also has limits. A long delay can be confused with a slow change in the source itself. Without a full set of clues, the geometry cannot be pinned down uniquely. Still, the scene remains stable in a quiet way. An arc that stays in place as background stars drift is not a random smear. It is a persistent route pattern around a concentrated mass. A gentle scale shift steadies the mind again. Near the dark center, the difference between one path and another can be a few horizon widths. Far away, those small differences project into arcs that span a large patch of sky. Minutes of motion near the inner region can correspond to years of drift in the surrounding field. The same geometry connects the near and the far without any new rule. The star field becomes a calm graph written in light. A final visual anchor closes this section. The pair of faint points hold steady while the connecting arc thins and brightens in slow waves. The dark region remains featureless. Only the paths around it carry structure. The scene eases from paths to origins since mass must be packed tightly to carve slopes this steep. The next section follows how a massive star can collapse and leave that concentration behind. A massive star can look tranquil while its deepest layers move toward a final change. A black hole forms when the center can no longer hold its own weight. The first scene is a bright star with gentle banding across its surface. Light pours outward in a steady wash. Beneath that calm, the interior is arranged in shells. A denser core sits inside. Around it, hotter layers keep transforming material. Fusion joins light nuclei into heavier ones and releases energy. That energy presses outward through heat and radiation. It supports the layers above against inward weight. The balance is quiet and exact. It resembles a geyser plume sustained by steady underground pressure. While pressure holds, the plume rises and spreads with a smooth shape. When pressure fades, the column settles back without warning. In a star, the fading does not begin at the surface. It begins deep inside, where fuel stages change and support weakens. This matters because support is the only thing delaying collapse. The second scene moves inward past the bright surface into opaque depth. Hot plasma becomes so dense that light cannot travel straight out. Photons scatter again and again in short zigzags. Their outward progress becomes slow. The core is hidden behind this luminous fog. That hiddenness sets a limit on observation. The final rearrangement in the center cannot be watched directly in light. Only the outer glow is visible after it has been mixed and softened by many layers. Inside, the core composition shifts. Each new stage produces less outward push for the same weight. The star can still shine with a calm face. The interior can still be losing the contest. A small understanding settles here. Brightness alone does not reveal the state of the core. The outer glow can remain steady while the center approaches instability. Core collapse is the rapid inward fall of a star's center. It begins when inward weight outpaces the outward push available. The third scene shows the core starting to contract. The outer layers still shine with almost the same color. Deep below shells slip inward and compress. The contraction is smooth at first. It is like a warm updraft that weakens in a calm sky. A column that once rose now slows, then settles. In the star, the inward motion gains speed because gravity strengthens as radius shrinks. Density rises. The gradient steepens from the outside toward the center. Layers that were separated become tightly stacked. Heat increases where compression is strongest. Another small unlock appears in the structure. Collapse is not a sudden vanishing. It is a tightening of layers and paths with the steepest changes confined to the deepest region. The plunge can be swift. The central collapse can complete in about 1 second, like a wave crest sliding past a single shore rock. In that brief span, the core changes more than the surface suggests. The fourth scene holds a contracting center that grows darker as it tightens. The surrounding shells lag behind, then rush inward after. Heat builds wherein falling layers compress and shear. The interior becomes a place of extreme pressure gradients. Yet the deepest region still cannot send a clean signal outward. Scattering remains thick. The brightest outward light still comes from higher layers. This is another limit of observation. The moment when the center crosses a final threshold does not announce itself in direct light. It is inferred from how the surroundings respond. At this distance, the next step is not a solid object forming in the middle. It is a condition that changes which paths exist. The event horizon is a boundary beyond which escape routes vanish. When enough mass is compressed into a small enough region, every outward route turns inward. The fifth scene shows this boundary forming without a seam. There is no edge made of matter. There is no crust. A smooth surface in space-time appears where directions change character. The physical detail lies in how curvature sharpens near that surface. Light paths that once passed through now bend into tighter arcs. Some routes loop and return. Some routes fail to turn outward at all. A quiet payoff follows from this geometry. The horizon is not detected as a surface. It is known by the disappearance of possible paths. Outside, the world remains full of motion. Inside, outward paths no longer exist. The sixth scene shifts back to the star's outer layers. They respond to the sudden deep change with waves that move outward through hot gas. Layers can lift and drift away into an expanding shell. The shell is thin. It is uneven. It carries filaments and clumps like smoke strands that stretch and fade in still air. Brightness forms soft gradients across the shell face. The center behind it grows quiet and dark. Any remaining glow comes from heated gas outside the new boundary. Nothing from inside the horizon contributes light to the outside story. Another limit appears here calm and clear. Different internal histories can produce similar outward shells. A smooth shell and a clumpy one can both fade into the same distant haze. The interior mass and spin cannot be read from shape alone. The last scene pulls back to a wider field around the new dark center. A thinning cloud drifts outward. Behind it, a background starfield bends into subtle arcs near the middle. Light roots gather into a faint curve that hugs close to the darkness. Farther out the field looks almost unchanged. Near and far coexist in one view. A compact boundary governs a much larger neighborhood. The section ends with a soft step toward the next checkpoint. The collapse has created the horizon as a clean boundary of roots. The next section lingers near that boundary and follows what light can still do there. At the edge of a black hole, the last light lingers in a quiet, disciplined way. The event horizon is the boundary where escape routes no longer exist. The first scene is close and still. A dark centre holds without texture. Around it, a thin veil of glowing gas drifts in slow arcs. The veil has a smooth gradient. It is brighter on the outer side. It dims inward until it vanishes into the black. No seam appears where the boundary lies, yet the boundary shapes every nearby route. A ray that passes outside can still curve around and leave. A ray that slips inside cannot find an outward direction again. The change is not a wall of matter. It is a change in what directions mean in that region. A small understanding settles early. The horizon is not a surface to be seen. It is a rule for paths. The second scene begins with a single bright knot in the inner veil. The knot flares, then fades. The flare is not observed as a clean spark. It stretches into a longer pulse as it departs. The pulse arrives dimmer than expected. Its colour shifts toward deeper red tones. The edges soften as if the light has been spread thin. Gravitational redshift is light losing energy while climbing out. Like waves climbing a shallow beach, crests spread and slow. Like a long swell meeting shallows, a sharp pattern becomes wider and gentler. This matters because the depth of the gravitational slope leaves a mark on the departing light. A deeper slope produces a stronger shift. Another small understanding follows without strain. A signal from near the boundary can fade away even if the source stays active. The fading comes from the climb itself, not from the source turning off. The third scene holds the same knot as it moves inward. Its orbit tightens. The track curves closer to the dark centre. The bright point circles and leaves a thin smear of glow behind it. The smear is not a full ring. It is a pale arc that thickens where the path bends most. The arc grows brighter for a moment when the point approaches the near side of the orbit. It then dims as the point swings behind the centre. The intervals between pulses grow longer at a distance. The glow seems to hesitate near the edge. The brightness declines in small steps. It steadies. It declines again. Motion near the boundary remains swift in its own neighbourhood. Collisions still happen. Heat still rises in the gas. Yet the outward record of those processes slows and stretches. The same orbit can feel like a quick loop nearby. It can look like a slow drift when judged by arrivals far away. A small payoff settles here. The horizon is approached without a final outward announcement. The outward light becomes weaker and more delayed. The approach can look endless from afar even when the local motion continues. The fourth scene moves to a narrow zone just outside the boundary. In that zone, light can almost circle the darkness. Photon sphere is a zone where light can orbit briefly. Like snow lifted into a small whirlwind, rays can loop once before they drift away. Like pollen caught in a slow spiral, eddy paths wrap and then unwind. This matters because looping routes pile up into a bright rim. In a simple non-spinning case, that zone lies about 1.5 times the horizon radius. It is like a sandbar just offshore from a steep coast. Light that skims the sandbar circles in a shallow arc before the tide carries it onward. Light that skims the photon sphere can circle once. It can circle again before it departs. Each near loop adds another layer of brightness to the rim. The rim can look sharper than the rest of the glow. It can also look slightly uneven because the glowing gas is not uniform. The physical detail is clear. A thin band forms where many near circular paths gather. Inside it, a darker region appears where paths fall inward. Outside it, the veil fades into softer haze. Another small understanding follows. The bright rim does not require a solid ring of matter. It can arise from geometry and repeated bending alone. The fifth scene focuses on what cannot be cleanly known. The deep region hides its interior behind the same rule that defines it. No outward light can carry a direct report from inside the horizon. Only outside light can be studied. Even that outside light has limits. Several bent routes can overlap before they leave. Their contributions blend into one pattern. Fine differences in path can blur together at long distance. Thin gas and dust between stars can scatter light and soften edges. A smooth rim can look thicker than it truly is. A sharp shadow edge can look rounded. The changing glow can also mislead. A longer pulse could come from deeper gravity. It could also come from a larger emitting region. A dimmer flare could come from redshift. It could also come from cooling gas. This is a limit of inference. More than one cause can fit the same outward shape. The limit does not erase knowledge. It sets the need for consistent clues. When pulse stretching matches colour shift and rim geometry, the picture becomes stable. The sixth scene returns to the veil and knot. The knot now skims close to the photon sphere. Its light splits into more than one route. One thread leaves directly. Another curves behind the dark centre and returns from the far side. The far side arrival is fainter. It is also delayed. The veil briefly shows two pale arcs at once. They are separated by a darker gap. The arcs brighten and then settle back into a single smear as the knot moves on. A new small understanding rests in this layering. Multiple paths can place the same source in more than one position in the sky. The duplication comes from curvature, not reflection. Paths are the visible story. The boundary remains unseen, yet it guides the entire scene. The section eases outward with a soft transition. Outside the horizon, and outside the photon sphere, longer-lived orbits become possible. Gas can circle many times and spread into a flattened layer. The next section follows that layer and explains how an accretion disk becomes the main lantern around darkness. A dim spiral can glow in silence while the centre stays black. It forms because falling gas keeps sideways motion as it sinks. The first scene is a narrow stream of gas drifting toward a dark region. The stream is thin at first. It curves as it nears the centre. It wraps into a flattened ribbon. The ribbon spreads into a pale wheel. The wheel brightens toward its inner rim. The outer parts remain smoky and faint. The shape is calm and simple. It is a disk built by rotation. Angular momentum is spin that resists changes in rotation. Like wind-stirred dust that keeps circling a shallow hollow, the motion persists even as space tightens. Like a drifting leaf that carries a swirl into a tighter bend, the sideways drift remains as the path narrows. This matters because inward motion must negotiate that stored spin. Most gas arrives with some sideways speed. That sideways speed grows more important as radius shrinks. The inward pull steepens. The circular drift tightens. The stream cannot keep a narrow shape for long. It spreads into a wider lane of orbiting gas. A small unlock settles into place. The disk is not created by gravity alone. It is created by gravity acting on rotating material. Gravity draws inward. Rotation keeps the fall from becoming direct. The result is a continuous compromise. A ring-like path forms where inward pull and sideways motion balance for a time. The ring is a crowd of nearby orbits. Where streams meet, compression warms the gas. Where layers slide, heating rises more slowly. The disk begins to glow from that work. The glow is not uniform. It carries bands and seams that drift through the rotation. The second scene moves closer to the inner disk. The glow sharpens. The rim looks like a bright crescent. A smooth gradient runs across the face. It is brighter near the inner edge. It fades outward into a wide, dim skirt. The disk also shows layering. A thin, bright skin sits above a darker midplane. The midplane looks like a soft lane of shadow. Dense gas blocks light from deeper layers. Only the surface glow escapes cleanly. Small patches flicker as hot lanes drift under cooler lanes. The flicker is gentle. It rises and falls like slow breathing in the light. Another small understanding arrives without strain. The disk can shine without touching the horizon. Most of the light comes from outside the boundary. It comes from orbital energy turning into heat. As gas moves inward, potential energy decreases. That energy becomes motion and turbulence. It becomes heat that light can carry away. The disk becomes a lantern that outlines nearby curvature. The center stays dark because inward paths still end at the boundary. The bright rim is an outside glow shaped by repeated bending and by fast orbital flow. The next checkpoint is the slow transfer of spin. Viscosity is internal friction that spreads motion between layers. Like two neighbouring sheets of fog sliding past each other, the boundary drags and mixes. Like fine sand layers shifting under a desert vortex, grains exchange momentum, and the pattern evolves. This matters because friction moves angular momentum outward. When some gas loses spin, it can fall inward. When other gas gains spin, it drifts outward. The disk becomes a conveyor of exchange. A quiet payoff follows from that exchange. Inward drift is usually small in a single orbit. The drift becomes meaningful over many loops. Gas can circle the centre many times before reaching the inner rim. The disk can look steady while individual clumps smear into smoother bands. The steadiness comes from averages across many paths. The brightness becomes a continuous field instead of a trail of separate knots. The third scene looks at the disk edge on. The disk becomes a thin, luminous line. A darker lane splits it along the middle. The top surface glows softly. The bottom surface glows softly. Between them, the midplane is thick with scattering. Light tries to leave and is redirected many times. The outward glow becomes smoother than the underlying motion. Another small unlock settles here. A calm surface can hide intense mixing below. The lane thickness changes with radius. It can look thicker farther out where the disk is cooler and denser. It can look thinner closer in where heat puffs the surface layers upward. One number anchors the scale. The hottest inner regions can reach about 1,000,000 degrees, like the heat inside a lightning channel. At that heat, atoms lose many electrons and the gas becomes a thin plasma. The brightest power shifts towards short wavelengths. Much of it leaves outside the visible band of light. The outer disk can be far cooler. It can glow in softer tones and broader layers. A gentle scale shift follows. Tiny collisions set the temperature. The same collisions repeat. They shape a disk that can span distances larger than a planet. The rhythm of change also stretches across time. Near the inner rim, an orbit can take only a few seconds. Farther out, an orbit can take days. Fast flickers can arise near the center. Slow waves can arise farther out. The glow can shimmer and then settle. A signal would carry many timescales layered together. The layering becomes a map of where in the disk the light originates. A bright ripple can travel inward as material warms. A dim gap can drift outward as spin is transported away. The scene stays quiet even while it evolves. A calm limit appears here. The disk interior cannot be seen directly in most bands of light. The midplane is opaque. The deepest layers are hidden by scattering and absorption. That hides the true density and the true turbulence. Several different internal patterns can produce the same smooth surface glow. A thicker disk and a thinner disk can look similar at distance. A hotter surface and a cooler surface can also mimic each other when the rim is blurred. This is a limit of observation and a limit of inference. The details of the hidden mixing are learned indirectly from the surface light. The final scene returns to the spiral from above. The inner rim is bright and tight. The outer disk fades into a wide, faint skirt. Spiral ripples move through the glow like slow waves in wind-blown sand. The ripples circle and unwind. The center remains an absence. The disk remains a visible boundary layer between darkness and the wider region. The section eases forward. The next step follows how the disk becomes more clearly stratified. The glow separates into hotter inner bands and cooler outer lanes. A rotating disk can look calm and uniform, yet its light carries a quiet map of depth. The disk becomes layered because heat and transparency change with distance from the dark center. The first scene is face-on and still. A dark centre sits inside a broad wheel of glow. The glow is arranged in pale bands that widen outward. The bands resemble patterns inside an agate stone. Each band holds a slightly different tone. The inner band is bright and nearly white. The outer bands fade into softer reds and then dim haze. Between the bands, faint seams drift as the disk turns. The glow is strongest near the inner rim. It weakens outward in a steady gradient. A small understanding settles early. The disk is not one temperature. It is a calm slope of heat spread across distance. Temperature gradient is a smooth change of temperature across distance. Like a planet with a warm equator and cool poles, the disk holds hot and cool zones at once. Like morning warming a sunlit ridge, inner zones brighten while outer zones remain subdued. This matters because temperature decides which light escapes most easily. In that region, heat is made by friction and compression. Gas in neighbouring orbits drags and mixes. The mixing is uneven. Some lanes heat more than others for a time. Those lanes drift onward and smear into broader bands. The second scene moves closer to the inner region. The bright band is no longer smooth. It has fine streaks that curve with the flow. A thin braid of brighter threads follows the orbit. A darker notch opens between two bright lanes. The notch closes again as the disk turns. The physical detail is clear. The glow is layered and striped. The stripes follow circular motion. Another small understanding arrives. The banding is a record of motion and heating, not a fixed structure. The next checkpoint is how light can escape at all from such dense flow. Opacity is how easily light passes through material. When opacity is high, light is trapped and scattered. Near the disk's central layer, density can become high enough to trap light through many collisions. The deepest glow becomes hidden behind its own material. Only a surface layer releases light cleanly. The third scene tilts the disk toward edge-on. The wheel becomes a thin, luminous line. A darker lane runs along the centre of that line. Above and below the surface, layers shine more evenly. The edges feather into faint haze as if the glow is brushed outward. The central lane stays darker because light there is scattered and absorbed before it can leave. A small payoff settles here. The brightest view is not always the deepest view. The surface can shine while the interior stays concealed. The hidden interior still matters. It controls how heat moves upward and outward. It sets how thick the glowing skin becomes. When density rises, the skin can become smoother and broader. When density falls, the skin can thin and show more texture. The next checkpoint is the way light carries a fingerprint of temperature. Spectrum is the spread of light across colours. A cooler surface glows more in deep red tones. A hotter surface shifts the glow toward paler and whiter tones. This matters because colour hints at where in the disk the light begins. The fourth scene returns to face-on. The inner band looks almost colourless. Just outside it, the band turns pale yellow. Farther out, it becomes orange and then deep red. The colours are not paint. They are the disk's heat written into light. The band changes are gentle. They do not jump sharply. The gradient moves like slow shading on a smooth stone. Another small understanding appears. Different radii contribute different colours. When those colours blend, the overall glow becomes a sum of many zones. Light behaves as a layered chorus. Each ring adds its own tone. The inner rings add the brightest and hardest light. The outer rings add softer light and wider haze. Even when the disk cannot be resolved in detail, the overall colour balance can still indicate how concentrated the heating is toward the centre. One number anchors the scale of change. Across the disk, temperature can differ by about 1,000, like the difference between fresh lava and cold basalt. The comparison does not require an exact value. It only marks how wide the range can be. This range creates a gentle scale shift in time as well. Close-in orbits are quick. Farther out, the same circular motion becomes slow. Brightness near the inner band can change on short time scales. Outer bands change more gradually. The fifth scene shows a bright patch in the inner band drifting forward. It brightens for a moment. It then thins into a longer streak. The streak wraps partway around the centre. It fades as it spreads. Farther out, a broader ripple moves more slowly. The ripple looks like a soft ring of shade passing through redder zones. A small payoff settles. Fast flickers tend to belong to smaller radii. Slow waves tend to belong to larger radii. The disk becomes readable as a layered clock, yet the reading is never perfect. A calm limit appears when trying to turn this map into exact structure. The inner regions are tiny on the sky. Their light can blend with light from slightly larger radii. Scattering above the disk can soften sharp boundaries. Thin dust in the wider region can also redden and dim the signal. Different combinations of disk thickness and temperature can produce similar colours at a distance. This is a limit of observation and a limit of inference. Surface colour cannot uniquely reveal the hidden density in the central layer. It can also hide the true shape of the inner rim. A sharper rim can appear smoother when blurred. A thicker disk can mimic a thinner one when seen through haze. The limit does not erase meaning. It sets how many clues must agree before a structure is trusted. When banding, timing, and colour shifts align, the disk's layered nature becomes hard to deny. Despite the limits, the disk keeps a stable rhythm. Surface layers brighten where heating rises. They dim where flow cools. The pattern repeats as new gas arrives and older gas drifts inward. Over long periods, the disk can persist while individual streams change. The final scene widens and quiets. The agate-like bands shrink into one pale glow around darkness. Beyond that glow, the surrounding region remains thin and cold. The next step follows what can rise from this layered motion. Ordered fields can thread through the disk and guide energy into narrow directions. A disk can glow as a wide wheel, yet a narrow beam can rise from its centre. Jets emerge when magnetic structure channels energy into tight directions. The first scene is calm and symmetrical. A thin disk lies like a faint coin of a light around darkness. Above and below, two narrow columns extend into black space. The columns are not solid. They are luminous threads with faint knots along their length. Each knot is a brighter patch inside the same straight line. The line stays narrow for a long distance. Its edges look sharp compared with the softer disk glow. The early anchor arrives at once. The disk provides heat and motion, then ordered fields guide part of that energy into beams. A small understanding settles inside that anchor. A wide flow can create a narrow outflow without any rigid pipe. The guiding structure is not a wall of matter. It is a pattern in fields that moving plasma tends to follow. Magnetic field is a region where moving charges feel a force. Like iron-rich sand aligning into arcs around a buried magnet, charged particles align into curved lanes around an invisible guide. Like mist shaped by a steady crosswind, a diffuse material can become a long, coherent plume. This matters because a jet is a flow shaped more by direction than by density. In that region, the disk is not perfectly smooth. The gas is hot and ionized. It conducts and carries fields with it as it moves. The second scene moves closer to the disk's surface. Faint loops and arcs of glow rise from the disk like translucent ribbons. They curve upward and then stretch. The ribbons do not stay open. They tighten and become straighter as they climb. The glow near the base is broader. Higher up, it becomes a thinner cord. A gentle payoff rests in this narrowing. The same field that rises from the disk can also squeeze the flow inward. Collimation is the tightening of a flow into a narrow beam. It resembles a geyser plume forced through a narrow volcanic throat. The vent spray is broad and chaotic. A short distance above the plume becomes a single column. The column stays narrow because sideways motion is damped by the surrounding structure. In the jet, sideways motion is damped by magnetic tension and by pressure gradients. The physical details remain visible in the light. The jet shows a bright spine and a fainter sheath. The spine is the most ordered lane. The sheath is a softer layer where mixing occurs. The brightness can change along the jet. Small knots appear like beads on a string. Those knots can form where the flow compresses. They can also form where the jet grazes a denser pocket of surrounding gas. The third scene shows one knot drifting outward. It brightens for a while. It then fades into the next knot. The spacing between knots is not perfectly regular. Some gaps are long and dark. Some gaps are short and crowded. Another small understanding settles. A jet can look steady while it contains many internal changes. The outside line stays straight. Inside, the flow can pulse and compress in cycles. The disk below continues to rotate. That rotation twists the magnetic structure anchored in the moving gas. The twist does not need to be extreme to matter. A gentle winding can store energy over time. The wound structure can guide plasma upward along a helical path. The helical motion does not always appear as a spiral in the sky. It can appear as a slight edge brightening on one side. It can also appear as a slow shift in where the brightest ridge lies. One number anchors the speed scale without strain. The fastest jet material can move at about 90% of the speed of light. That is like crossing the distance between Earth and the Moon in a little more than a second. The comparison is only a scale marker. It does not require exact timing in any single system. A scale shift follows from this speed. Near the base, the jet begins in a region smaller than a planet. Far from the base, the same beam can stretch beyond the size of a star cluster. The origin is compact. The reach is immense. The beam stays narrow because the guiding structure extends with it. Yet the guiding structure is never perfectly stable. The fourth scene zooms in on the jet edge. The boundary looks like a thin, luminous skin. Small ripples run along it. Some ripples fade quickly. Some grow into small kinks. A kink can brighten as it compresses material. It can then relax and straighten again. Another small payoff rests here. A jet can self-correct without any rigid frame. Magnetic tension acts like a stretched cord that resists sideways bending. When the jet edge wobbles, the field lines can pull it back toward the axis. At the same time, too much twist can trigger instabilities. The flow can develop a corkscrew-like pattern. The beam can remain directed while its interior writhes gently. The fifth scene returns to the disk and the base region. A faint funnel-shaped glow rises from the inner disk. The funnel narrows toward the axis. The disk surface below shows bright lanes. Those lanes slide and shear. Heat rises where lanes rub. Some of that energy stays in the disk and radiates away. Some of it is guided upward along field lines. The jet base is not a single point. It is a region where disk field and gravity interact. The interaction is quiet but intense. The physical picture is consistent. A wide rotating layer generates and drags magnetic structure. The structure opens above and below the disk. The opening offers a preferred direction. Plasma follows that direction more easily than any sideways path. The sixth scene holds a long view. The twin beams extend into a sparse medium. The beams carve narrow cavities. Around each cavity a faint cocoon of disturbed gas forms. The cocoon is dim and wide. It looks like a soft shadow wrapped around the bright line. The cocoon grows gradually as the jet deposits energy into its surroundings. Another small understanding settles into this long view. Jets are not only features near the black hole, they shape regions far beyond the disk. They can heat distant gas. They can stir it into filaments. They can create lobes of faint glow where the beam slows and spreads. Even so, observation meets a calm limit. The magnetic structure that guides the jet is not seen directly. Field direction must be inferred from how light is oriented and from how patterns repeat. Fine details near the base are also hard to separate at great distance. Many layers overlap along the line of sight. Bright knots can hide fainter lanes behind them. Surrounding dust can scatter and dim the beam edges. Different internal field shapes can produce similar straight jets. This is a limit of measurement and a limit of inference. The outer beam reveals only part of the inner order. The final scene quiets again at the centre. The disk continues its slow-layered glow. The twin columns remain narrow and persistent. The knots drift outward and fade. The beam remains a disciplined line drawn through darkness. The next section follows the source of the twist itself. Rotation near the black hole changes the nearby geometry and reshapes what it means to remain still. A dark center can remain silent while the space around it carries a quiet twist. A spinning black hole drags nearby space-time, so many paths turn with it. The first scene is wide and calm. A dark oval rests inside a pale ring of disk light. Far behind it, the star field refuses to stay as points. Many stars stretch into small curved commas. Each comma leans in the same direction. The bending is weakest at the edge of view. It grows stronger toward the oval. At this distance, the twist appears as a mild shear in the background. The pattern is gentle, yet it persists. A small understanding settles. Rotation can reveal itself in the paths around darkness, not on darkness itself. The second scene moves closer to the inner disk. Bright lanes circle the darkness in tight curves. Fine streaks appear within the glow. They lie along the direction of orbit and shear. One side looks sharper and slightly brighter. The opposite side looks softer and dimmer. The contrast remains mild. It comes from rapid motion and from light climbing out of deeper gravity. The disk also shows a smooth gradient. Brightness increases toward the inner rim. The rim stays thin and ring-like. Another small understanding settles. Motion and gravity sculpt brightness together even without any sudden flare. Frame dragging is rotation twisting space-time and nudging all motion to turn. A slow, rotating glacier offers a calm parallel. Fine snow lines on its surface begin nearly straight. They bend into arcs as the ice turns around a basin. Near the center, the bending is strongest. Farther out, the lines relax and straighten. No external push is needed. The shear of motion shapes the pattern. In the same way, nearby paths acquire a shared drift around the axis. Orbits that would prefer one plane can be guided into a slow change of orientation. This matters because dragged space-time shifts where stable motion persists near the inner rim. The third scene introduces a boundary that is not the horizon. A faint shell surrounds the oval where turning becomes unavoidable. Ergosphere is a region outside the horizon where stillness is impossible. Thin ice plates on a broad rotating current never remain fixed. Even when a plate drifts outward, it still slides along with the turn. A pale foam line on the same current also curves around the center. This matters because the ergosphere separates free drifting from compulsory co-turning. Outside that shell, a path can in principle avoid rotation. Inside it, every route carries some swirl. One number anchors the thickness of that shell. In a rapidly spinning case, the ergosphere can extend to about 2 times the horizon radius near the equatorial plane. That is like a narrow surf ring widening into a beach. The comparison is only a sense of thickness. The exact width depends on spin, yet the idea stays stable. The horizon is a thin boundary of escape. The ergosphere is a broader zone of forced drift. Another small understanding settles here. A clean edge can be surrounded by a wide belt where direction is already decided. The fourth scene returns to light near the inner rim. A faint knot of glow travels around the center. Its light takes more than one curved route outward. One thread leaves on a direct path. Another thread swings behind the oval and returns from the far side. The returning thread arrives later and dimmer. For a short time, the bright rim looks braided. 2 arcs overlap, then blend back into one. The braid is not a material rope. It is a brief stacking of roots. A quiet payoff follows. Multiple paths can make one object look doubled even when nothing splits. The ring becomes a record of curved travel. The curvature grows where dragging is stronger. The curvature weakens where the field relaxes outward. A gentle scale shift steadies the mind. Close to the horizon, a small step inward changes behavior quickly. A path that circles safely a little farther out can become unstable deeper in. Far from the center, the same step in radius changes almost nothing. Over seconds near the inner rim, brightness can flicker and smear into streaks. Over thousands of years farther out, the overall axis can remain almost unchanged. The near region is fast, the far region is slow. The same rotation links both through the geometry of the surrounding space. A calm limit appears when trying to know the spin directly. The horizon cannot be seen turning as a surface with trackable features. No outward light carries a direct report from inside the boundary. Even the ergosphere does not show a visible edge. It is inferred from patterns in motion and from the ring and disk shape. Several different conditions can mimic each other. A thicker disk can imitate stronger dragging by changing brightness around the rim. A tilted disk can imitate an asymmetry that looks like rotation. Fine differences in spin can also be hidden by blurring in the ring. When light from many radii overlaps, the signature becomes mixed. This is a limit of observation and a limit of inference. The twist is learned indirectly by consistency across many signs rather than by a single clear marker. The fifth scene lifts above the disk again. Two narrow beams rise along the axis. Near their bases, the glow shows a slight spiral texture. A short distance higher, the beams straighten into long columns. Faint ripples travel along the edges. Some ripples brighten into knots and then fade. The knots drift outward and leave the bases quiet again. Another small understanding settles. Spin and dragging can cooperate with ordered fields in hot gas and guide energy into narrow directions. The beams remain narrow even as the disk stays broad and layered. The section eases outward one last time. The starfield commas relax back into points. The bright crescent around the shadow softens into a steadier ring. The jet knots drift outward and grow faint. The axis remains as a calm geometric fact. The next section follows a different kind of motion. When two black holes share an orbit, space-time itself can carry away a travelling pattern with no light at all. Two dark masses can circle in silence, yet the surrounding space carries a faint travelling pattern. Gravitational waves carry energy away as ripples in space-time itself. The first scene is distant and spare. A pair of dark circles drift around a shared centre. No surface details appear. Only motion is clear. The circles trace a slow spiral that tightens over time. Around them nearby dust forms a thin haze. The haze stretches into curved lanes, then relaxes again. The stretching is slight, like breath moving a veil. A calm hook rests in that softness. The change is not light. It is the geometry that light later must cross. The early anchor follows at once. When two black holes orbit, their changing gravity can launch waves through the universe. A small understanding settles early. The orbit does not last forever. Energy leaves the system through the waves. The loss makes the orbit shrink. The second scene moves closer. The circles are nearer now. Their orbital path speeds up. The surrounding haze becomes more structured. A faint oval region forms around the pair. Within it, motion looks smooth but urgent. The space between the circles compresses and releases as they pass. The compression is not a material squeeze. It is a change in distances measured by geometry. Gravitational wave means a travelling stretch and squeeze of space-time. Like a calm swell passing under floating seaweed, spacing rises and falls without carrying the weed away. Like a gentle ripple moving across a field of tall grass, alignment shifts while the ground remains. This matters because the wave can move through empty space and still change distances. The third scene pulls back to a wider view. A thin ripple front expands outward from the orbit. It is not a bright ring. It is a faint pattern in how space measures itself. Stars in the background remain steady points. Yet their apparent separations drift minutely as the ripple passes. A line of faint stars seems to widen then narrow. The change is subtle and brief. Another small understanding appears. The wave affects distance in two perpendicular directions at once. One axis stretches while the other compresses. The pattern alternates as the wave travels. No medium is required. No material surface is needed. The fourth scene returns to the orbiting pair. The spiral is tighter now. The track resembles a coiled thread being drawn inward. The coiling is smooth, not jerky. The time between each orbit shortens. The surrounding haze becomes hotter and thinner. A faint bright arc appears where gas is stirred, then it fades. The main story remains the geometry. As the orbit tightens, the wave grows stronger. The spacing shifts become larger. The rhythm becomes faster. Another small payoff settles. The wave carries a signature of the changing orbit. The pattern in time reflects how quickly the pair is spiraling inward. In that region, the signal is a rising tone in geometry. It begins low and slow. It becomes higher and faster. The fifth scene zooms in on the last moments before contact. The dark circles are almost touching. Their outlines remain clean against the dim haze. The orbital motion becomes a blur. Space around them seems to tremble. The ripple fronts leaving the system become closer together. The wave cycles can reach about 100 cycles each second, like the rapid flutter of a small insect wing. The number is only a scale marker. It marks how fast the rhythm can become near the end. Another small understanding arrives. Faster cycles imply a tighter orbit and a smaller separation. A gentle scale shift follows. Over billions of years, two black holes can drift closer through interactions in a crowded region. In the final seconds, the remaining separation collapses quickly. The long, slow history funnels into a brief final spiral. The sixth scene holds the instant of merger. The two dark outlines become one. The surrounding haze flares in its motion then settles. A single dark circle remains. Its edge looks slightly distorted at first. The distortion smooths out as waves carry it away. Ring down is the settling of the merged black hole into a stable form. Like a struck bell that stops wobbling and returns to stillness, the shape relaxes through a fading sequence. Like a pond surface after a stone sinks, the last ripples spread and weaken until calm returns. This matters because the settling pattern encodes the mass and spin of the final black hole. Another small payoff lands inside the calm. After merger, the system is simpler than before. One horizon remains, one spin remains. The wave pattern shifts from a rising rhythm to a fading one. The fade is smooth and short. The geometry becomes quiet again. The seventh scene shifts outward again to follow the waves. The ripple fronts expand across the starfield. They pass through thin gas without much change. They pass through dust lanes and dark clouds. The waves do not scatter like light. They are not absorbed by dust. The pattern remains faint but persistent across great distance. Yet another limit appears soft and clear. The wave cannot be photographed as a visible ring. The space-time stretching is far too small to see directly in a starfield. Its presence is inferred from how consistent the timing and pattern are across many cycles. Even then, distance can be hard to pin down. A stronger signal could mean a closer source. It could also mean a more massive source farther away. Without additional context, more than one scenario can fit a similar pattern. This is a limit of measurement and a limit of inference. The wave carries clean information about rhythm. It carries less direct information about exact scale without other clues. The eighth scene returns to the merged black hole in its quiet state. The disk haze, if present, reorganizes around the new gravity. Faint arcs of light bend near the center. The surrounding starfield returns to a steadier arrangement. The black hole itself remains unseen in its interior. Yet the merger has left an imprint on the wider universe through the passing ripple. Another small understanding settles. Black holes can announce themselves in more than one language. Light traces disks and rings. Space-time traces waves. Both are indirect. Both are powerful when they agree. The section eases toward the next checkpoint. After waves reveal motion, and mass light returns to reveal shape. The next section lingers on the shadow and the bright rim that outlines it, and on what that outline can and cannot confirm. A dark silhouette can appear sharper than any glowing gas around it. The shadow is a shape made by missing light paths near the horizon. The first scene is quiet and close. A broad crescent of disk glow wraps around a dark center. Just outside that crescent, a thinner hairline ring appears and nearly closes. The hairline ring looks almost too narrow to hold. It brightens in short segments, then settles into an even rim. The dark center is not a hole in matter. It is an absence created by rotes that do not return. Shadow is the dark silhouette formed by captured light paths, like the empty centre of a smoke ring outlined by its own swirl, like a hollow in drifting snow that looks dark because flakes fall inward. This matters because the silhouette traces gravity without revealing any interior surface. A small understanding settles early. The shadow edge is not the event horizon. It is set by paths that skim past the centre and barely escape. Those paths define a critical outline in the sky. Light behaves as if the region offers only a few safe corridors. Outside those corridors, rays are turned inward and never reappear. The second scene slows down and holds the rim. The bright crescent has a smooth gradient. It is brightest near the inner edge. It fades outward into faint haze. The inner edge is not a hard wall. It is a blending zone where many curved routes overlap. Some rays arrive from the near side of the disk. Some arrive from the far side after bending around the dark centre. The overlap makes a thin, bright ridge. That ridge sits just outside the shadow. Another small understanding arrives. The shadow is enlarged by bending. The outline looks bigger than the horizon because rays that pass near the centre are strongly redirected. For a non-spinning black hole, the shadow spans about 5 times the horizon radius. It is like a small hole in soft bread that looks wider when the crust sets its outline. The number is a scale marker. It ties an invisible boundary to a visible silhouette. A gentle scale shift follows. The horizon can be smaller than a mountain range in width. The shadow can still occupy a noticeable patch of sky when seen from far away. Between those scales, the same geometry controls every route. The third scene brings out finer structure. A second, even thinner ring appears outside the first hairline ring. It is fainter. It flickers in small arcs, then fades. That ring comes from light that loops more than once before escaping. Photon ring is a thin band from light looping near darkness, like a whisper that returns after circling a quiet canyon, like a thread that wraps around a spindle before sliding free. This matters because repeated loops stack into an extremely narrow line. The narrowness is a clue to how close those paths pass to the critical zone. Another small payoff settles. The photon ring is not the same as the disk in a rim. It is a geometric feature created by many nearly circular routes. Even if the disk changes, the ring location stays nearly fixed. Its brightness can change. Its position stays steady because the critical bending stays steady. The fourth scene shows time passing. The bright crescent shifts slightly around the shadow. The crescent brightens on one side, then the bright region moves. The motion is smooth. It resembles a slow glow travelling along a curved shoreline at dusk. The shadow remains centred and calm. The hairline ring remains in place even while the crescent changes. Another small understanding arrives. Much of the image is an average. Glowing gas is restless. Turbulence can rearrange brightness on short timescales. The geometry that sets the shadow changes far more slowly. A distant view therefore mixes the quick and the slow. A single snapshot can catch a bright knot in one location. A longer view tends to smear that knot into a broader arc. The shadow outline is the calmest part of the whole pattern. The fifth scene turns to the physical details at the edge. The boundary between brightness and darkness is not perfectly sharp. It has a soft shoulder. The shoulder comes from blurring in many overlapping rays. It also comes from scattering in thin plasma between the source and the far field. Scattering redirects some rays by small angles. It washes out the finest lines and thickens the ring. Another small payoff settles. A thicker ring does not always mean a different black hole. It can mean the same geometry seen through a softer medium. A bright crescent can also broaden when emission rises from a thicker layer of gas. Several causes can mimic one another in the final image. This is a clear limit of observation. Fine angular details can be smaller than what a distant view can separate. It is also a limit of inference. A similar shadow and ring can arise from different arrangements of hot gas around the same central mass. The sixth scene explores that ambiguity in a calm way. The crescent can be bright on the lower side, It can be bright on the upper side. It can even break into two separated arcs. The shadow remains nearly round. The photon ring stays near the same radius. Yet the crescent shape changes because the gas flow changes. The brightness depends on density and temperature and motion. Those vary with time. Those also vary with the thickness of the emitting layer. Another small understanding arrives. The image is a combination of geometry and weather. Geometry sets where routes can go. Weather sets which routes are lit. The shadow is the geometric frame. The crescent is the weathered paint. The seventh scene widens and shows a background star field behind the shadow. Several stars near the edge appear doubled. A faint arc bridges 2 points like a thin strand. That strand brightens, then fades as the source drifts. The arc is a lensing feature made by the same bending that creates the shadow. Another small payoff settles. The shadow and the lensing arcs belong to one family of effects. Both arise from curved paths. Both reveal the presence of strong gravity. Yet both can be blurred by the same mixing of roots. The exact brightness of arcs can change with background structure. The shadow outline stays more stable because it is tied to the capture of paths. The eighth scene returns to the inner rim and its softness. The ring edge can never be infinitely sharp in practice. Light from slightly different heights and radii overlaps in the final view. The emitting gas can be spread across a thick region. Rays from deeper layers can be absorbed before leaving. Rays from higher layers can escape more easily. The result is a layered brightness profile, not a single thin line. Another calm limit appears. The interior of the shadow cannot be used to map the horizon directly. No light comes from inside. The darkness holds no internal structure. Any apparent texture inside the shadow would come from noise or from imperfect subtraction of surrounding glow. This is a limit of observation in the strictest sense. The interior offers no direct signal at all. The ninth scene eases into the larger scale again. The shadow becomes a small mark within a much wider disk. The disk becomes a faint smear within a galaxy field. The galaxy field becomes a thin pattern in a larger darkness. The same rules apply at every scale. Paths bend. Some paths return. Some paths fail to return. The shadow is a calm boundary between those fates. The section ends with a soft turn toward forces that act across small distances. When gravity changes rapidly from one point to the next, shapes can be stretched into long strands. The next section follows these tidal gradients and shows how they sculpt gas near the inner regions. A quiet field of gravity can become a sculptor when its strength changes sharply from one point to the next. Tidal stretching arises because gravity is stronger on the near side than the far side. The first scene is a faint star drifting through a dark region. Its light is smooth at first. As it approaches a deeper well, its outline becomes slightly oval. The oval lengthens along the direction toward the centre. A thin haze forms around it, then peels into a narrow ribbon. The ribbon curves in a shallow arc and begins to trail behind. The early anchor settles at once. The most dramatic shaping comes from a gradient, not from an absolute pull. Tidal force is the difference in gravity across an object. Like a soft slab of wet clay set across a small ledge, one side sags more than the other. Like a mist sheet over uneven ground, the low spots thicken while the high spots thin. This matters because the same object can be gently held in one region and torn into a stream in another. The second scene slows down near the closest approach. The star's light is no longer centered on one rounded shape. It spreads into a bright head and a long tail. The tail is layered. A brighter spine runs through its center. A fainter sheath surrounds it like smoke around a spark. The spine shows knots where the ribbon compresses and brightens. Between knots, the ribbon becomes thin and dim. A small understanding arrives. Stretching does not happen evenly. It happens in pulses where the path bends and the stream folds. The ribbon begins to wrap around the dark center. Its inner edge curves tighter than its outer edge. A smooth brightness gradient appears across the ribbon width. The side nearer the center is brighter and hotter. The far side is cooler and more diffuse. The physical detail is clear. The stream carries a sharp inner boundary and a feathered outer edge. The third scene pulls back to show scale. The ribbon can extend about 1 million kilometers, like about 40 times around Earth. The number is a calm marker for length. It shows how a single compact source can become a vast filament. A gentle scale shift follows. The shaping begins over seconds near the closest passage. The resulting stream can persist and orbit for years. A small unlock settles inside that shift. A brief encounter can create a long-lived structure. The stream continues along its orbit after the initial stretch. Parts of the ribbon move faster on the inner track. Parts lag on the outer track. The ribbon therefore shears. It becomes thinner in places and thicker in others. Where it thickens, heat rises and light brightens. Where it thins, the glow becomes transparent and faint. The fourth scene moves closer to one knot in the spine. The knot looks like a bead of light set inside the filament. It brightens as it compresses. It then spreads into a longer streak as the flow pulls it onward. The bead does not remain a point. It becomes a wave in density that travels through the stream. Another small understanding arrives. A stream can carry memory of its own formation as moving clumps and gaps. The stream also begins to curve into a returning loop. Part of it swings past the center and comes back toward the region where the disk would lie. The returning part intersects with slower material and compresses again. Compression forms a brighter arc where two lanes meet. The arc is thin, its edges show a soft, scalloped pattern. The scallops are small ripples in density. The fifth scene introduces the calm boundary between order and confusion. Close to the center, the stream is so thin and fast that small disturbances grow quickly. A slight sideways drift can widen into a larger bend. The bend can produce a new knot. The knot can split into smaller knots. Another small payoff settles. Complexity can emerge from simple gravity once the stream becomes narrow and sheared. Yet the overall motion remains governed by a single rule. The stream follows the paths allowed by the curved region. It wraps it, intersects, and it spreads. The glow that appears is a byproduct of compression and friction within the stream. It is not a light from the black hole. It is a light from gas doing work as it is rearranged. The sixth scene holds the region where the returning stream nears the disk plane. A faint ring of hot gas begins to form from repeated crossings. The ring is incomplete at first. It looks like a partial halo of vapor. Over time it fills in. The halo thickens into a wider lane. Its surface becomes smoother than the filament that feeds it. Another small understanding arrives. Tidal streams can seed an accretion flow by delivering gas on intersecting paths. The flow becomes more circular as it loses some of its original directed motion. A calm analogy fits this transition. A magma filament stretched between two cracks can drip and then collect into a slowly circling pool. The filament is narrow and uneven. The pool is broader and steadier once it gathers. This matters because the same material can look violent as a thread and calm as a disk even when the physics remains continuous. A limit of intuition appears softly here. It is tempting to imagine the stream as a single rope with a single tension. The real stream is a layered sheet with thickness and internal gradients. Different layers move at slightly different speeds. Some layers cool and become transparent, some heat and shine. The stream is not one line. It is a bundle of lanes that overlap in projection. The seventh scene addresses the limit of observation with the same calm. At a great distance, the filament cannot be seen as a three-dimensional ribbon. Only the integrated light along the line of sight is available. Knots can hide fainter lanes behind them. A brighter arc can be an overlap of two sheets rather than a true compression. Dust between stars can scatter light and soften the stream edge. Even the stream length can be hard to confirm. A longer tail could mean a closer passage. It could also mean a different viewing angle. The same brightness profile can come from different densities if the thickness is unknown. This is a limit of measurement and a limit of inference. The stream is learned from its changing glow and its changing shape, not from a direct view of every layer. The eighth scene returns to the geometry near the centre. The tidal gradient steepens rapidly with decreasing distance. The near side of the filament experiences stronger curvature than the far side. The result is a twist in the filament cross-section. One edge rolls inward. The opposite edge lags and fans outward. The filament develops a slight corkscrew texture along its spine. The texture appears as alternating bright and dim patches along the length. Another small payoff settles. Even without any external disturbance, differential gravity can generate internal twist and layering. The filament therefore becomes a factory of structure. It produces knots, gaps, and intersecting arcs. Each intersection is a chance to shed energy as heat and light. Each shed makes the orbit slightly more circular. Over time, the flow can settle into a disk that shines more steadily. The ninth scene pulls back to a larger neighbourhood. The disk that forms is only one outcome. In some cases, the filament remains too thin and disperses into faint haze. In other cases, the returning loop feeds the inner region and brightens the rim. The same tidal process can therefore influence the brightness and the supply of gas. It can also create outward disturbances when heated gas expands and pushes into surrounding material. The final scene quiets again. The long ribbon fades into a smoother lane. The knots become less distinct as they smear into a more uniform glow. The dark centre remains unchanged in appearance. The surrounding region carries the record of tides as shape and light. The next section follows what that shaping means on even larger scales, where black holes influence the structure and temperature of their wider environments over long spans of time. A black hole can stay visually small while its influence spreads through an entire galactic core. Energy released near the centre can travel outward and reshape the surrounding gas into cavities and ripples. The first scene is wide and dim. A galaxy core appears as a faint fog of hot gas. The fog has a gentle brightness gradient that peaks near the centre. Inside that glow, two darker hollows sit on opposite sides of the core. Each hollow has a rounded edge. Each edge is traced by a thin, brighter rim where gas piles up. The hollows look like paired dimples pressed into a luminous cushion. The early anchor settles at once. The central engine alters its environment mainly by pushing on gas, not by lighting it. The second scene holds on the rim of one hollow. The rim is a thin shell with a smooth curve. Just outside it, a faint ripple arcs outward like a slow wave in mist. The ripple is broader than the rim. It fades with distance. Along the rim, small filaments appear where denser gas resists the push. The filaments look like torn threads. They trail behind the rim and then dissolve. A small understanding settles. The hollows are not empty in a simple sense. They are regions where hot gas is displaced and pressure is rearranged. Feedback is energy from the centre altering the surrounding medium. Like a bubble rising through thick mud, a low-density region can expand and lift heavier material around it. Like a deep breath swelling a thin membrane, pressure can carve a rounded void without leaving a hard boundary. This matters because a cavity records how energy moves through a larger scale than the disk. The third scene moves inward toward the base of the hollow. A narrow channel links the hollow to the central region. The channel is faint and straight. Its edges are slightly brighter than its interior. The channel widens gradually as it climbs. The widening is smooth, not jagged. The channel looks like a corridor cleared through fog. Another small payoff settles. A narrow outflow can inflate a broad cavity once it meets a softer region. The cavity grows because pressure inside stays higher than pressure outside. The rim expands as a shell. The expansion slows as it meets denser layers. The shell can remain coherent for long periods. It can also develop wrinkles where density varies. A bright ridge can form where the shell compresses a denser clump. A dim gap can appear where the shell slips into a lower density pocket. The fourth scene widens again to show the pair of hollows together. The two cavities are not perfectly identical. One is slightly larger. One has a sharper rim. The surrounding fog shows a mild asymmetry. A thicker band of gas lies on one side of the core. A thinner band lies on the other. The cavities push into these bands and inherit their differences. Another small understanding appears. The environment shapes the cavities as much as the cavities shape the environment. A cavity in a uniform medium would look like a near-perfect bubble. A cavity in a layered medium becomes lopsided. The rim brightens where density is higher. It fades where density is lower. The center does not need to change for the shape to change. The next checkpoint is how these shapes translate into heat. Shock is a compressive wave that heats material as it passes. Like a distant thunderfront pressing through a cloud deck, a shock can add heat, without leaving a lasting mark at one point. Like a long swell steepening into a breaking line, a gentle pressure wave can become sharp where conditions change. This matters because a weak shock can keep hot gas hot even when cooling tries to soften it. The fifth scene follows a ripple moving outward from the cavity rim. The ripple is faint but broad. It wraps around the core like a shallow arc. The arc is brighter on its inner edge. It fades gradually on its outer edge. The brightness pattern indicates compression that is mild and spread out. Another small payoff settles. Heating does not require a violent blast. Repeated weak compressions can offset cooling over long spans of time. The sixth scene shifts to a longer time scale. The cavities persist and drift. Their rims rise through the surrounding medium like buoyant pockets. The central channel becomes harder to see as the cavities move outward. The hollows remain as darker ovals with bright edges. Their motion is slow compared with disk motion. 1,000,000 years can pass like the time a large river can carve a deep new bend into rock. Over that span, the cavities can travel far from the center. The shell can thin. The rim can fray into filaments. Yet the hollow can still be traced as a faint depression in the glow. A gentle scale shift settles in. Near the horizon, changes can occur over seconds. In the galactic core, the same energy can leave marks that last for millions of years. The seventh scene focuses on the boundary where the rim meets a denser layer. The rim presses into a sheet of gas. The sheet buckles. It forms a fold that looks like a soft ridge. The ridge is brightest along a narrow crest. Just behind it, a darker lane forms where gas is evacuated. The fold then relaxes and spreads sideways. Another small understanding arrives. The environment becomes structured by pressure waves and cavities, not only by gravity. The gas can be kept from collapsing inward too quickly. It can also be stirred into new patterns. Filaments can form where cooling and compression meet. Voids can remain where pressure stays high. The core becomes a tapestry of gradients and shells. The eighth scene introduces a calm limit. The cavities are seen only through the light of the surrounding gas. Their true depth depends on how much gas lies along the line of sight. A shallow cavity viewed edge-on can resemble a deeper cavity viewed face-on. The rim brightness depends on density that is not directly visible. The age of a cavity depends on its rise speed, which depends on pressure and viscosity that are uncertain. Several histories can produce similar shapes. This is a limit of observation and a limit of inference. The cavity is a shadow in hot gas, not a solid bubble with a measured wall. Yet the limit does not erase meaning. When paired cavities, channels, and ripples appear together, the case for feedback becomes coherent. The ninth scene returns to the core as a whole. The cavities fade into the broader glow. The central region remains the brightest. The brightness gradient remains smooth overall. Inside that calm, shells and ripples record repeated episodes of pushing and heating. Another small payoff settles. The black hole does not need to shine constantly to matter constantly. Intermittent outflows can leave long-lived structure. Each episode can refill the same pattern of hollows and waves. Over time, the environment becomes regulated. Cooling is slowed. Inflow becomes less direct. The core stays hot and diffuse rather than collapsing rapidly inward. The section eases forward with a soft transition. The next section follows how this long-term regulation links to growth and history, and how mass and spin accumulate over cosmic time without any need for steady feeding. In some galaxies, the darkest center changes quietly, while the outer stars keep wide and steady orbits. A black hole grows and turns through accretion and merges across cosmic time. The first scene rests on the core of a spiral galaxy Viewed from far above its plane, faint lanes of gas curve inward. The lanes are thin at first and then thicken into a soft spiral. Near the centre, the spiral becomes a smooth oval glow. The glow shows a bright inner rim and a softer outer shoulder. The rim looks like a thin band of light that stays sharply defined. The shoulder fades outward with a gentle gradient. Small clumps drift along the spiral lanes and dissolve into the glow. Accretion is matter drifting inward while shedding energy and angular momentum. It resembles droplets that add mineral layers inside a cave. Each droplet leaves a trace, and the trace hardens into a new film. Over time, the films build a longer form without any single dramatic step. Another small payoff arrives. A long-lived black hole can gain much of its mass by quiet layering. The growth can be smooth in appearance even when the supply arrives in pulses. The second scene moves closer until the glow becomes a ring around a darker centre. The ring is not perfectly uniform. One side is brighter and thinner, the opposite side is softer and broader. The inner boundary stays crisp like a cut edge. The outer boundary looks brushed as if light scatters through a thicker layer. The physical detail stays steady for many orbits. A small payoff settles. The crisp inner boundary traces where stable motion becomes difficult for the hottest flow. When that boundary sits closer, the heat is concentrated into a smaller region. The third scene holds on the ring's slow turning. The bright side drifts slightly an angle while the thin side stays thin. The thicker side remains thicker and more diffuse. The pattern suggests rotation and shear within a layered flow. Spin is the black hole's rotation described by angular momentum. Like a vortex in water that tightens when rotation is higher. Like a rotating column that keeps its shape when the swirl is steady. This matters because rotation shifts how close the hottest layer can circle. Rotation also shapes how strongly light bends near the inner edge. The fourth scene widens and introduces a second compact glow. Two galactic cores approach in slow motion. Each core carries its own ring-like light and its own faint halo. Between them a bridge of gas stretches like a translucent ribbon. Along the ribbon, brighter knots appear where gas compresses into denser patches. Around the pair, long arcs of faint stars curve outward. The arcs are smooth and thin, and they fade at their tips. Another small payoff arrives. A merger can add mass in a step rather than a layer. A merger can also change spin by bringing in orbital rotation that does not match the old axis. A gentle scale shift follows. Near the inner ring, brightness can rearrange over seconds or hours as turbulence shifts the emitting layer. In the merging core, orbital tightening unfolds across millions of years. On the scale of a galaxy, tidal arcs persist far longer while they drift and fade. The fifth scene returns to the moment when the two compact glows nearly overlap. The bridge becomes narrower. The surrounding halo brightens into a shared envelope. A faint spiral ripple appears in the envelope as gas responds to the changing gravity. The ripple shows a sharp leading edge and a softer trailing wake. A small payoff lands. The same physics repeats across scale. A sharp edge marks rapid change and a soft wake marks gradual mixing. The sixth scene focuses again on growth by accretion. The inflow does not remain constant. A long quiet span can pass with only a faint ring. Then a new stream arrives along one lane. The ring thickens and brightens. The halo becomes more luminous and more extended. After the supply fades, the ring thins and the halo softens. Over about 100 million years, repeated episodes can add substantial mass. The process resembles a drip building a noticeable ridge on cavestone. Another small payoff arrives. Time-averaged growth can be large, even if any single bright phase is brief. The seventh scene turns to how spin responds to the direction of arriving matter. Gas arriving in a steady plane can torque the rotation into alignment. The inner ring can shift inward as the rotation increases. Gas arriving in misaligned clumps can tug in changing directions. Rotation can rise and then be partly cancelled by later infall. Mergers can tilt the axis again through their orbital geometry. The ring's asymmetry can carry hints of that history. Yet a calm limit enters and stays gentle. At the smaller scale, the glowing layer is a thin skin on a thicker stream. Beneath that skin, cooler matter can carry most of the mass. The skin can brighten or dim without changing the deeper supply very much. A small payoff settles. Brightness alone is a poor measure of long-term growth. At greater distance, the core glow can be softened by dust and by intervening gas. Fine structure can blur into a single patch of light. That blur hides whether the inner edge is truly sharp or merely unresolved. The inner ring is not a literal wall in space. The glow depends on temperature and density. It also depends on how light escapes through surrounding layers. Different thicknesses can mimic different inner edges. A tilted structure can mimic a more compact one. Rotation cannot be measured directly. It is inferred through models that can share similar brightness patterns. The distant past cannot be watched as a continuous story. Only separated snapshots exist across distance and epoch. When rings and bridges appear alongside tidal arcs, a coherent growth history becomes more plausible. The final scene returns to a single calm core after the disturbance. The tidal arcs have spread and faded. Faint shells of starlight linger as broad arcs far from the centre. Gas that once formed the bridge settles into a new rotating plane. The shared envelope has relaxed into a smoother halo. The central ring remains as a thin band around the darker centre. The inner edge stays crisp. The outer edge stays feathered. The glow is steady enough to feel quiet again. The section eases forward. The next section widens further to long consequences and to slow shaping across deep time. A distant darkness can announce itself without any light at all. Gravitational waves carry information about changing gravity across space. The first scene is wide and quiet. Two compact dark centres orbit within a faint haze of thin gas. The haze is smooth and pale. It forms a soft oval around the pair. As the orbit tightens, the oval becomes slightly pinched. Two brighter arcs appear on opposite sides, then fade. When mass moves fast and curves strongly, space-time can carry a travelling ripple. The ripple is not made of particles or light. It is a moving pattern of tiny stretch and tiny squeeze. The second scene moves closer. The two dark centres trace a tight circle. The gas blur stretches into a thin ring. The ring shows a sharp inner edge and a softer outer gradient. One side looks brighter and thinner. The opposite side looks dimmer and broader. The changing brightness hints at rapid motion and strong bending of light. Yet the clearest message can come from the ripple itself. Gravitational waves are ripples in spacetime that travel outward. In plane imagery, spacetime behaves like a frozen lake surface. A distant crack sends a long wrinkle sliding across the ice. The wrinkle is not a moving object. It is a moving pattern across the surface. The pattern carries energy away from the orbit. Losing energy tightens the orbit. Tightening the orbit strengthens the ripple. The third scene widens again. The orbit is now a point within a field of dust filaments. The filaments form a loose lattice with uneven spacing. As the wave passes, the spacing shifts in alternating bands. One band draws neighbouring strands slightly closer. The next band separates them slightly more. The change is brief, and then it is gone. The wave does not push dust outward. It changes the distances between nearby points for a moment. The direction of that change is not fixed. As the orbit turns, the stretch axis slowly rotates. A filament that tightens in one band can loosen in the next. The pattern repeats with growing speed as the pair spirals inward. A signal would travel at the speed of light. Its wavefront expands as an ever larger shell. Near the source, the pattern changes quickly. Far from the source, the shell becomes broad and smooth. The fourth scene follows that shell into a quiet nebula region. A thin mist of gas shows faint parallel striations. The striations look like wind-drawn frost in cold air. As the shell passes, the lines bend into shallow curves. The curves reverse and then relax. The bending is strongest where the gradient of the ripple is steepest. Energy leaves the orbit as waves. The orbit shrinks and speeds up. The waves grow stronger and change faster. The process accelerates toward the final moment. Then the final moment arrives and passes. The fifth scene holds on what remains. Two dark centers become one. The surrounding ring of gas wobbles and then smooths out. The inner edge stays crisp. The outer edge stays feathered. The new black hole settles into a stable outside shape. The settling produces a brief sequence of diminishing oscillations in space-time. It resembles an ice ridge that trembles after a sudden shift. The tremble fades as the ridge stiffens. The fading oscillations reveal the remnant mass and how fast it turns. They do not reveal a map of anything hidden beyond the boundary, where light no longer returns. Only the outside influence is available. A gentle scale shift follows. The merger itself can finish in a short span. The wave then travels for about 1 billion years, like the time a continent can drift across an ocean basin. During that travel, the source can long since be quiet. Gas can settle into a new disk. Stars can rearrange within the host galaxy. Yet the wave keeps moving through emptier regions. The sixth scene rides with the wavefront in intergalactic space. The background is sparse and dark. Faint starlight threads appear as distant arcs. The arcs remain steady while the wavefront passes through. Light behaves as if it follows the curved geometry it encounters. A wave changes that geometry slightly and briefly. The seventh scene shows a narrow beam skimming past a dark core. The beam forms a thin, luminous arc. As a wave passes, the arc shifts in thickness. It becomes slightly sharper, then slightly softer. The change is temporary. It leaves no permanent mark in the light itself. Waves can modulate other signals without adding new light. A quiet limit of observation appears and stays specific. This stretch and squeeze are extremely small compared with any familiar size. Over a distance as wide as a planet, the change can be smaller than a single atom. Such a subtle shift is easy to confuse with other motions. Turbulence in gas can distort shapes. Intervening gravity can blur arcs. Several different mergers can produce similar wave patterns once distance is unknown. Orientation can also hide key features by projection. The ripple still carries only a small set of gross facts. It carries the total mass scale and the pace of the final tightening. Fine structure in the surrounding gas can be erased from the wave shape. A signal would be mixed with countless weak sources across the sky. At great distance, only a compressed summary remains. The eighth scene turns from one event to a quiet population. Across a cluster, many mergers occur at different times. Their waves overlap into a broad background. The background is like wind passing through a forest canopy. It appears as a general sway, not a single branch motion. This matters because a background sets a floor on what can be separated cleanly. Even so, the larger story remains clear. Mass gathers and reorganizes across eons. Some of that reorganization is recorded in passing ripples. The last scene returns to the calm core of a galaxy. The central dark region sits inside a gentle halo. A thin ring of gas circles in a stable plane. Dust lanes spiral inward and then fade. Far beyond old tidal arcs are barely visible. The system changes across ages that are difficult to hold in one thought. Between those ages, the passing ripple leaves a quiet imprint. The section eases forward with no sharp edge. The next section settles into a softer landing and a wider stillness. A black hole can feel like an absence that still shapes the sky. The unseen boundary reveals itself through bent light and through a shadow carved out of surrounding glow. The opening image rests in deep space. A distant scatter of starlight sits behind a compact mass. The background does not stay uniform. It stretches into arcs. It closes into a thin ring. The ring is pale and nearly circular. It has bright segments and dim gaps. Those changes do not require a surface. They come from paths of light that curve then reunite. At this distance, gravity behaves like a gentle guide for trajectories. A ray that would have missed the center instead skims past and turns. Many such rays arrive from different directions. The result is a luminous loop around an empty point. A small understanding settles here. Curvature can draw an outline in light even when the centre stays dark. The ring becomes proof of influence without contact. The next image moves closer. A broad disk of hot gas turns around a darker centre. The disk is layered. The outer glow looks soft and wide. The inner glow looks thin and sharp. Brightness rises toward the middle, then drops into a hollow. A faint rim of light appears close to that hollow. It seems to hover just outside the deepest darkness. Light behaves as if it circles before it leaves. Some paths wrap around once. Some paths wrap around more than once. Each wrap adds distance and dims the light. That is why the rim stays thin. It is made from rare paths that linger then escape. Another small understanding settles. A bright ring does not mean a solid ring exists. It can be the same region seen along many curved routes. The disk becomes a backlight. It lets the darkness draw a boundary with gentle contrast. A term can enter softly and then dissolve back into plain language. Event horizon is the boundary where escape becomes impossible. It is like the lip of a smooth waterfall. Upstream water still looks calm and ordinary. Downstream flow cannot climb back over the edge. The comparison stays imperfect, yet it holds one point. The boundary is not a wall. It is a one-way line for motion and for light. From far away, the boundary never sends a final flash. It simply stops contributing new light. A small understanding settles again. The horizon is defined by what cannot return, not by what can be touched. The disk can glow right beside it, yet the horizon itself remains unlit. A single number anchors the scale without strain. For a stellar black hole with several times the sun's mass, the boundary span can be about 30 kilometers. That is like the width of a broad canyon. It suggests how small the boundary can be. The gas disk can extend far beyond that. The dark influence can shape paths across a much larger region. In that contrast, the scale shift feels natural. A canyon-wide boundary sits inside a structure that can span worlds. The disk continues to turn. Its inner edge brightens. Its outer layers fade. Fine filaments of glow shear and stretch. A physical detail stays clear. There is a gradient in brightness. There is a sharp change in thickness near the inner edge. There is a curved rim where the ring concentrates. The shadow itself becomes the central quiet. It is not a hole punched in space. It is a region where fewer light paths reach far away. Some paths fall inward and never emerge. Some paths bend away. Some paths arrive after looping and arrive faint. Together they draw a dark patch. The patch is rounded. Its rim is not perfectly hard. It softens because the background glow is uneven. It softens because light can skirt the edge by many distances. One side of the surrounding ring can look brighter. The brightness can come from motion within the disk. A small understanding settles without hurry. A shadow can carry information about gravity even when the horizon stays hidden. The darkness is not empty. It is a map drawn by missing routes. A limit of intuition arrives and stays specific. A common picture expects a sharp edge like a cliff line. In reality, the ring and shadow depend on the glow that backlights them. The glow is turbulent. It flickers and knots. Brightness changes can smear the rim. Distance blends fine structure into a soft patch. Because of that, more than one flow pattern can produce a similar crescent. The constraint comes from resolution and from incomplete backlighting. Only indirect signatures remain. The horizon itself never appears as a line. It appears as a boundary in what can be reconstructed. A small understanding settles here too. Limits are part of the phenomenon because the boundary denies direct return. The earlier starlight ring returns for a final time. Now it is seen as two long arcs. They mirror each other across the empty centre. One arc is sharper, one arc is softer. That difference hints at uneven brightness in the distant source. It also hints at how sharply curvature changes with radius. In that region, a slight change in path can mean a very different bend. Light behaves as if space itself is a lens. The lens has no glass. It has only curvature. Arcs describe the mass without showing it. They let darkness be inferred through structure and surrounding light. A small understanding settled again. Evidence does not need a direct image of the boundary. It can arise from distortions that repeat across many scenes. The final image widens and slows. A spiral of dust and gas turns gently in a host galaxy. Near the center, faint glow gathers. Farther out the glow thins into haze. Yet the same rules remain. Paths of light curve. Some paths return. Some paths do not. The event horizon stays defined by escape. The shadow stays defined by missing routes. At this distance, the scene can rest on that simplicity. A boundary can be real without being seen. A presence can be known through the shapes it allows. The scene settles into a steady night. The arcs fade back into the starfield. The disk glow softens. The darkness remains calm and unmoving as the story eases toward quiet rest.